So I'm very honored to introduce our first speaker, Navid Shahriari, who is a Senior Vice President at Intel, where he has dedicated an impressive 35 years of his career. Currently, Navid is slated to lead Intel Foundry's technology development team. What sets Navid apart is his breadth of experience. His extensive contributions span across delivering various products, design portfolios, EDA, leading test development, validation, and significantly improving power and performance. Please welcome Navid.
Thank you very much, Tom, and good morning to all of you. It's a real honor for me to be here. I'm delighted that I was asked to share my thoughts in this wonderful and exciting time for computing. It's an honor to be among such talented and luminaries from the industry as well as the academia. So thank you for having me. The AI era is amazing, is upon us. I was reminded of it yesterday. I was actually checking in at the hotel, and the person that was checking me in asked why I was here. They understood that I'm here to give one of the presentations. And he started talking about the power of AI and the fact that there's not enough energy in the world and how we should think about making dome-shaped data centers and geothermal cooling, and there was a lot on his mind. And of course, I didn't have a lot of expertise in much of what he was covering, but I know that the problem is real and it's being recognized by everyone. How many of you recognize this image? A handful? An amazingly famous Japanese, about a 200-year artwork. It's a woodblock print. You've probably seen it across many domains on T-shirts and so on. And it depicts the amazing and overwhelming power of nature. You could see Mount Fuji in the back. You could see the big wave. And every time I see this image, I get reminded of this overwhelming power of AI that's upon us. It is amazing in its scale. It's revolutionizing everything we do, and will continue to really advance the state of the art. But it's also really challenging our industry in every term possible, in building systems that scale in power, performance, energy, and cost at unprecedented levels in my career, 35 years. The training compute, the need for training compute flop has grown at an amazing 1 million-fold in 1 decade. Just think about this, 1 million-fold in 1 decade. To put that in perspective, I don't know how many of you remember the internet, which also reshaped the world. I'm sure you remember the internet, but about a decade ago, I remember I was excited that I had a 5 megabit internet speed at home. A decade later, only a decade later, you have a few gigabit speed at home, probably if you live around an advanced area, which is 1,000-fold. Quite amazing. But comparing that to the training compute growth of 1 million-fold, it really pales in comparison. So the AI force is here. It's bigger and more comprehensive than anything any of us have seen in the past. With that in mind, the progress that we've made in scaling capability, in my opinion, has been brute force. And we've basically thrown a lot of dollars, a lot of resources, a lot of additional dollars and capability at this. And if you look at this matrix, from silicon to packaging to interconnect and power delivery, all of the things that you know and love and work in, I assume, we've really tackled the power and the need of AI in these domains. But the progress across this matrix is really absolutely necessary. We need to be able to make progress across each one of these boxes, but making great progress in each box is not going to be sufficient. We need to do more. I work, and myself and my team of amazing talent and engineers work at the hardware portion of the matrix. This is where I will start. That's where there's quite a bit of progress that's been made across Intel Foundry as well as the rest of the industry. So that's where I will start. Silicon scaling has been at the core of the industry revolution for multiple decades. And silicon scaling effectively gives us more performance for a given unit of energy. And the density gives us more transistors, and more transistors get used to get more features and more wonderful things that we do with it. And so silicon scaling perhaps is one of the most important part of this matrix. At Intel, we're in high volume production on Intel 3 technology in the middle of the page. We've got multiple families of products that are shipping in high volume. And then we started introducing the 18A technology, the Angstrom era. And the 18A technology for us represents a very significant 15% perf per watt advantage over the Intel 3. And as you can see, there are many derivatives of the various technology nodes, 18A, 18AP, as well as our next major node, 14A. And so the technology continues to scale, it gets advanced, it gets better, more power efficient, and there's a lot more wonderful things that you can do with it. In the Angstrom era, we introduced ribbon-fit transistors in our 18A capability. It's the largest innovation since the FinFET. If you look at this ribbon-fit area, there's really two fundamental revolution, one around the transistor and the one around the interconnect. On the transistor, the ribbon-fit technology is quite a large inflection point, and the gate all around, as you can see in the middle of the page, basically the gate surrounds the channel and gives you much better electrostatic capability control, which enables significant enhancements in power and performance for a given area. And you're able to reduce Vmin, the voltage that your device can operate in, providing capability to be able to build more low-power devices and capabilities. And with that, as you do scaling, the scaling enables you to be able to get more features and enable capabilities like zettascale computing. For example, you can get increased memory capacity and bandwidth. You can enable large compute clusters. You can enable major accelerators, and fundamentally lowering the latency and improving energy efficiency gives all of our creators ability to create new and wonderful things. The second major innovation in this area is power via, which, in my opinion, it's the largest innovation in the interconnect since the copper wire was introduced in the 1990s. And you can see on the picture on the left, I hope you can see it. I know there are many monitors here. In a traditional stack, you have the transistors at the bottom, and then you've got interconnect at the top. The interconnect's responsible for all of the signal, as well as power and ground layers that are needed for interconnecting the transistors across. And with the power via, basically what happens is the transistor is now in the middle, sandwiched between two sets of interconnect, signal at the top and power and ground at the bottom. And I don't know if it looks simple to you. It's quite innovative. It's a work of art. And I've had the pleasure of designing two major products on this technology. The first one in silicon being in high volume validation, and will be introduced to the world early next year. And the second one is in the fab. So I've got quite a bit of experience in this domain. And having the ability to have signals at the top and the power and ground at the bottom. I don't know if you could see the metal stacks are thicker at the bottom. Gives the thicker metal gives you basically lower loss, but much more efficient for transmitting power. And then you can optimize your signal layers for what you really need at the signal. And so the result is dramatically more efficient in power and enables your standard cells to really scale. without having to shrink the metal pitch. A very, very large innovation here. And so you get utilization improvement, you get performance improvement, and about 3 to 4% switching power reduction, which is quite impressive. But with PowerVia, while we revolutionize the ability to really scale and get benefit, there's also some capability challenges that it represents. Now that you have the transistors sandwiched between two sets of densely packed metal layers. And so, the traditional infrared imaging, being able to isolate fault and repair or understand them is highly compromised. So at the Intel Foundry, we've been advancing the state-of-the-art in fault isolation and debug capability from thermal signal imaging for fault isolation to having surgical openings to be able to leverage E-beam to be able to see through the transistors and logic state and to be able to identify faults and be able to understand and address them. And you can see some of the work of art there, and you can see the image on the right. I don't know how many of you have seen transistors switching. Here's a voltage contrast. You can see right 0 and right 1 transistor switching, and with these techniques, you can actually see down the wire and a fin level and be able to isolate issues and be able to debug them. So quite an advancement. I don't know how many of you seen this. I can never get tired of watching this image. It's pretty cool, seeing transistors switching on and off. Another area of significant advancement is in and around high-NA EUV. High-NA EUV is giving us a very compelling advantage over traditional EUVs that were just implemented a couple of generations ago. And since many of you probably are not familiar with looking at these images, I'll explain a bit about this. If you look at what high-NA EUV does, it enables direct print and eliminates the need for multi-patterning. And so as you do the direct print, you could see the line and space in the picture on the left, and effectively you could see contact and holes in the middle after etch. And you could see the selective deposition where you can have line where you'd want to be with depopulation schemes. So the pictures you see and the results are on a real test chip with OPC printed on our high-NA EUV and our D1 facility that I'm very proud to be a part of in Oregon. This technique not only gives you the direct print gives you the ability to reduce the number of exposures and do single steps as opposed to multi-patternings, multi-exposures, and long steps. So it gives you reliability improvement, manufacturability improvement, but also, being able to do direct print and not having all of the extra metal reduces the parasitic capacitance of a circuit and gives you energy efficiency with this kind of depopulation and selective print. So quite proud of this achievement, and you'll hear a lot more about this over the many months. But that's not where we end. I only have 30 minutes today and many hours, so I'll whet your appetite with a couple of additional things that are in our research and development pipeline, and you'll hear more about them in this conference in some of the additional talks. The image on the left is the industry-leading 6-nanometer gate length. It's about 3x gate length reduction compared to the typical gate-all-around that you see today. And it's industry, this capability has industry-leading short channel effect. The picture in the middle is our first gate all-around 2D transistor with gives you a dramatic 2x NMOS current over the published results that we've done. It's quite fascinating to see this work that gives us the ability to continue to scale over many generations of technology. The picture on the right It's a little wavy on the picture because of how thin the sample needs to be in the TEM that we do. But it's the very first HVM-compatible subtractive roux process. You could see the subtractive roux process at the bottom gives us the ability to have really tight metal pitch for our M0. And then you could see the next metal copper landing exactly where we need to land. Gives us the ability to really reduce our min pitch for our metal zero. Quite an amazing work of art, and gives me confidence that we can continue to scale our interconnect with this capability. And so computing is all about cost per flop of compute, and over the last 50 years, the cost per flop has reduced pretty dramatically through a lot of innovations like the ones that I covered in the previous pages. And that mission continues for all of us in the industry. The cost per flop needs to continue to drop and will continue to drop due to all of the innovations that the industry, as well as all of you in academia now and in the future, will do. And so what happens as the cost per flop continues, you get denser and more capabilities, and all of the homogeneous integration happens on silicon. But over the last several years, we've seen the growth of heterogeneous integration as the advanced packaging capability has improved significantly. I've been in the industry for a long time, and this is one of those amazing transformation that I think will give the future generations of engineers and developers a lot more to play with. And so with advanced packaging, without the general penalty of advanced packaging, you get the ability to basically put discrete capabilities and IPs on a process node that's the most beneficial for that node, based on IP availability, based on the capability and cost structure of a given node. You can get to reuse one IP from one process to the other, and then you basically stitch them in a very efficient manner on a package, just like I'm showing. And over the years, as the packaging capability, especially in the last 10 or so years, has advanced, we are seeing the heterogeneous overall market growing. And in fact, it's projected to be about 30% of all of the packages that are shipped in about 10 years or so, as you can see in the graph. And so when it comes to packaging, in the old days, people talked about packaging and said, just make sure that it's robust and reliable. And it was all about interconnect density, and we wanted to continue to scale the density of packaging. But the interconnect power efficiency has taken the industry by a storm and has really enabled integration that I didn't even think were possible even a few years ago. On the graph, you could see at the bottom, it's the standard package that probably you've seen in all of your favorite devices. There are many, many standard organic packages that are there. And typically you see things like a 100-micron bump pitch. You could see about the chip-to-chip power efficiency is measured by picojoules per bit of data that gets transmitted, and about a half a picojoules per bit was kind of the industry norm. And as you move up, we introduced the EMIB packaging technology, and we have many generations, a couple of big data center families of products, not only for us, but also in the industry running. And you can see the bump pitch scaling to sub 50 microns, and you get a dramatic improvement in about a 3x bump density improvement. So you get more bumps for a given area. And then we introduced 4-rows chip-on-chip package, and then the 4-verse direct and future 4-verse direct technologies that are in our pipeline. You could see the bump pitch scaling to already less than 10 microns and going all around 1 or sub 1 microns. And with an interconnect density of less than 10 microns, you get about 10,000 bumps per millimeter squared area. So with these advancements, both in terms of interconnect density as well as power improvement, the tax for advanced packaging, heterogeneous integration has reduced pretty dramatically. And this is why you see all of the innovations and why advanced packaging is playing such a critical role. Other advancements in packaging has to do with off-package, being able to get data in and out of the package. And it's all about optical integration. We started with kind of connectors that connected to the packages for optical I/O interconnect, and then we started inventing on-package optical I/O capabilities, and then fully integrated optical I/O. And just if you look at the shoreline bandwidth density that these packages will give you, we've gone from 100 megabits per millimeter of package area to more than 8 terabits per second. So dramatic improvement in bandwidth density and energy efficiency over the years with these optical interconnects on package. As the individual at the hotel reminded me, the power for data centers continue to go up. So this is a typical data center GPU. And you can see the power is dramatically increasing for a typical GPU, 800 watts, 1,000 watts, 2,000 watts, and continues to scale. And with this power, you'll have to figure out how to deliver power and then into a device, into a die, into a package, into a system, and then figure out how to actually remove the power. Power delivery is an area that we spent quite a few years advancing the state of the art at Intel, and I know many industries, many people in the industry work in this domain. There are many ways of delivering power, but ultimately, the metric that matters is end-to-end efficiency of the input power into a given device to how much of the power is being actually used in the system. And so if you look at the linear regulators, they're quite robust. They've been a workhorse for many applications. But because of the fact that these linear regulators they have a very small difference between the voltage in and voltage out. They're not very efficient at the higher wattage or higher power applications. So this is, in fact, created a need for the integrated voltage regulators. At Intel, we've been working on fully integrated voltage regulators where we stack two devices in one of our nodes. And be able to get basically a significant power efficiency. You could see our 1.8 volt fiber in that blue line on the graph. And then we continue to push the technology, stacking 3 devices on our 18A capability, second generation fiber with 2.4 volt. And you could see even getting more efficiency upwards of 80% even at 800 watts. And working on high voltage GaN-related voltage regulators that you'll hear more about, and to continue to advance the capability in this domain and get even closer to 85% efficiency. Of course, we've had advancements in magnetic inductors and MIM caps that really help aid power delivery and power efficiency. So a lot of advancements in this area. The other area that's equally important, if not more challenging, is basically the integrated thermal heat removal material. So if you really think about this, the thermal interface material, or TIM, is such an important part of the overall package and system architecture. When you have metallic TIMs, you want to make sure that your bond layer thickness is thin, you have no voids to be able to have real good thermal efficiency. But there are challenges as some of the BGA packages get surface mounted and go through very high heat. And so at Intel, we've been creating some industry-leading metallic as well as polymer TIMs to be able to not only withstand the overall thermal cycles that you get during capabilities like surface mount, but also be able to continue to be robust over the life of a product. The other area that I would tell you in this thermal area that's quite amazing and there's good progress that's being made is in and around building a rapid concurrent thermal power performance modeling. I'm quite proud of this capability. I've been a recipient of using this on some of the products that I've owned at Intel. And being able to model the thermal gradient in a transient state and be able to make changes in your models to really remove the hotspots gives you a dramatic capability, cooling effect during dynamic transient that reduces the overall need for exotic cooling, as well as it enables your circuit to run cooler and more efficient. The other area of innovation is in and around our thermal interface material. If you look at the innovations that we've had for our integrated cold plate that you can see on the right, a significant increase in cooling that's applied directly at the board level and the system level. So a lot of innovation in and around power delivery, thermal interface materials, as well as all of the cooling that needs to happen. I'll switch gears quickly since I'm running out of time. There's this big timer that says you're running out of time and on the stage here. And so when it comes to being able to make these heterogeneous capabilities, having interconnect I/O capabilities is really critical. And UCIe is a consortium. It's a capability spec that Intel donated to the industry. I think there was initially Intel and 9 promoters. Now we have an industry around with more than 135 member companies with UCIe. And one of the key factors driving the UCIe adoption is really this standard being adopted at a very rapid pace. It basically its ability to enable performance as the bump pitch scales. And so with bump pitch scaling, you get much and much better performance with UCIe. And the UCIe is quite amazing. The team that developed this capability has been in my group, and I've implemented it across many families of products like the picture that I'm showing you here. This is a example of an integrated, just about everything that I just talked about all in one picture. Of course, I didn't want to show you an actual product. There are many, many products that we have as well as are in the industry where you've got integrated silicon, as you could see. It could be a CPU or a GPU, advanced packaging capabilities. You could see the interconnect. You could see UCIe memory on the side. You could see SerDes and your I/O interconnect, and you've got UCIe-A, UCIe-S, 3D vertical stacking, all of this being integrated. So it's a work of art, but it's also a work of fantastic engineering, and it's already powering many of us in the internet. So quite proud of this work, and I think this is the type of capability that gives me reasons to believe that we can continue to scale and continue to advance together as an industry. Couple of other silicon-based capabilities beyond kind of classical computing that I wanted to talk about. One is the neuromorphic computing on the left. You could see the Intel Lohi 2. This is actually a Sandia Labs hollow point. It's quite amazing to see. This is kind of inspired by the human brain. It's a very different approach to computing. It gives you a dramatic 100x energy efficiency and 50x faster capability. And we just need to accelerate the emerging algorithms to really get the benefit of the energy efficiency of this capability. On the right, you see quantum. There's a lot of chatter, a lot of exciting happenings, news in the industry about quantum. You can see a number of the quantum scientists at Intel here in this conference as well. And every time somebody talks about quantum, I get excited. It's really fantastic to see us really advance this capability for future generations of technologists and users. The big challenge in quantum is really around scalability. And at Intel, our quantum program, I'm biased, but I'm pretty excited about the capability that we have at Intel. And the quantum computing, the scalability that we have at Intel is based on our years of experience in CMOS fabrication, being able to build these qubits on CMOS and scale them. That's the best way to scale. Today we have hundreds of billions of transistors on a chip, and the same thing will enable the quantum revolution for many years to come. The interconnect between the control electronics and qubit is really the main bottleneck. We've leveraged our highly integrated cryogenic CMOS for qubit control, also leveraging our most advanced packaging technologies to be able to put the large density of IOs that are needed together. We've developed a cryogenic PDK to design optimized for operating at 4 Kelvin. And we've used multiple generations of these cryogenic control chips in our own. We've got 2 PDKs already released, one for the cryogenic control and the other one for the qubit. So a lot of exciting advancement in this area. And every time we'll come to this conference, we'll even share more advancements with you. As I started, this solid wave is upon us. It's all over the place. And the hardware lays a good foundation, but it really doesn't address the 1 million-fold that we have in the need that we have in this compute for AI. So what's the answer? The answer is we need to make progress across each one of these individuals, but we also need to figure out how to co-optimize this matrix together, and no single one of those boxes that I showed you is going to help address this 1 million-fold. We must work together. We need to collaborate as industry and academia, and to be able to navigate this big AI challenge that's upon us. The models continue to get bigger and wider. They have more need for compute and software and capability and security, and we really need to collaborate as an industry. And this is why I'm excited to be here, because of some of the best and brightest people here in the academia as well as the industry. So we need a matrix that's really co-optimized. So how do you co-optimize this matrix? I don't know how many of you are familiar with design and process technology. I assume most of you are. In the early days of integrated circuits, I'm old, so I remember earlier days than most of you probably remember. But in the early days of integrated circuit, significant advancements were made easily just by pitch scaling and geometric scaling alone. And then over the years, as the scaling was becoming more and more challenging, the litho engineers started to learn about circuits and design. And they learned that the designers, the circuit designers, basically assemble these transistors in these logical primitives, NAND, scan flip-flops, NOR, and so on. And these collections basically were termed as standard cells. And as you continue to scale standard cells and figure out how to become more and more efficient, the idea of shrinking the standard cells and at the block level, it's still a big thing today. In fact, we call it DTCO, or design technology co-optimization. It's a big area, big focus that provides a ton of benefit for us. And so system-level technology co-optimization, or STCO, is really the natural progression of what we've been able to do on DTCO. And you want to be able to make progress at every individual level, but also co-optimize the entire system together. And that's really the only way that we can get ahead of this big wave of AI, in our opinion. The path to STCO is complex, but it starts with really early system planning. That's maybe the biggest challenge. You need EDA tools and capabilities. You need to be able to partition your designs and be able to create all of the optimization points, including all of the thermal and power delivery capabilities that I mentioned. And then enabling the next phase of it is enabling agility and modularity, is being able to assemble the various parts of the modules together to be able to do rapid prototyping and making changes. And then ultimately, the breakthrough will come as you optimize that entire system for the workload that you have in mind. around the edge, around the data center, around anything that you believe that you need to optimize for. And so this is really what's absolutely necessary for us to be able to get ahead of this big AI wave. And so we are in San Francisco Bay Area. I don't spend a lot of time in San Francisco, thankfully, for all the traffic and all of this stuff that's going on. But this is like the epicenter of all of the startups. This is really, and for every startup, you have to have a clear value proposition for anything that you're pitching. And the value proposition for what I'm talking about here is that for the customers, which are many of our collective customers, they want to basically maximize the return that they have for an invested system environment that they have. But right now, they're gated by long turnaround times to be able to do their workload and optimize it across the stack. There's really a lack of rapid prototyping and capability across the system level. So this STCO framework and platform offers an agile, comprehensive framework that's really fast and enables an ecosystem support for a differentiated technology option that everybody will need for a fast time to market. So with that, I will tell you that each of us plays a critical role in this domain, and we need to really continue to work together to advance the industry's innovation frontier, because the need is clearly there, and together we can really do some wonderful things to get ahead of this wave. And with that, I'll just end here by explaining that the wonderful engineers in our company have 10 papers here. You could see them here. They will get into a lot more depth into some of the areas that I covered. I only had 30 minutes. I overran. I apologize. So if you like any of these areas, I recommend that you check them out. I think you get a lot out of them. Thank you. I appreciate it.